Okay, welcome to Unit 2 on filters and Note Set 2 in the Digital Audio Signal Processing course. In the last last video, we did a general characterization of filters for audio, and in this note set, we're going to be talking about some of the classic things for analog filters that are used in audio. We're not going to hit everything, but we'll hit some of the most important things. There is some coverage of some of this stuff, particularly in the Zolzer book, but not all of the stuff in this video is from that, just maybe the second half of the video. So you might be wondering, hey, this is a digital audio course. We're doing DSP. Why are we talking about analog or continuous time filters? Well, I've alluded to this already in previous note sets. What happens mostly in discrete time or digital audio processing is we're asked to mimic some of those classic analog filters because they sounded great and that's what people like to hear. And so if we start understanding what those things are, those analog filters, we can then come up with ways to make discrete time filters that mimic those. So that's the idea. And this really simplifies the design process for those discrete time filters. We start with some known good continuous time filter that we may set out to say, I want to make something that sounds like that. And then we can apply something called the bilinear transform. And we'll cover that in the next note set, but it's a simple way to take a continuous time transfer function and convert it to a discrete time transfer function. So all those classic filters, analog filters, we know the transfer functions for them. So it'll just be a matter of applying the bilinear transform to it. And then you have a discrete time filter, which is pretty straightforward to implement. We're going to talk a little bit about a specific class of filters called Butterworth filters. So, we characterize filters as low pass, high pass, shelf, peak, and so forth. That's one way of slicing up the world of filters. The other way of another way of slicing up the world of filters is the mathematical characteristics of the transfer functions. And those are often named after people. So Butterworth was an engineer who came up with a particular type of design for a particular type of filter. And those are now known as Butterworth filters. They are very commonly used as the continuous time filters in audio because they have this nice characteristic of what's called maximally flat. I'm not going to go into the details of what that actually means, but it just means that the pass band is nice and flat, doesn't have ripples, and it doesn't drop off too fast as it heads out to the cutoff frequency. So if you want to go into more detail, there's lots of reading on analog filters, and you can read all about Butterworth filters and what that maximally flat really means. Butterworth filters are also monotonically decreasing in the stop band. They just keep going down, 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 down. And in fact, once they hit the cutoff frequency for a low pass, for example, the nth order Butterworth filter will drop off at n times 6 dB per octave. And you may remember from a signals and systems class doing Bode plots or something like that in a control systems course. You may have learned about 20 dB per decade. Well, 6 dB per octave is the same thing, just written a different way. Remember, octave is a doubling and decade is a factor of 10. I know it seems weird. This should be 8 since this is saying dec and it's 10. Octave should be 8, but it's not because it's borrowed from music where the octaves in a scale have fundamental frequencies that are just a factor of 2, a doubling. Okay, so there are other filters, filter classes. So Chebyshev, another name of somebody who didn't really design filters but worked out mathematics, and then somebody used that math to design filters. So they're called Chebyshev filters. They there's two types of those, and you can check those out. One type has ripple in the pass band, but is monotonic in the stop band, and the other is monotonic and nice and flat in the pass band, but then bounces up and down in the stop band. So, and then there's other ones. There's Bauer filters and elliptical filters and so forth. So the world of audio is perhaps filled with all of those, but I really think the Butterworth filter is the most common. So we're going to look at that more than the other ones. And back in the review, I showed how to make some of those discrete time versions of Butterworth and Chebyshev and elliptical. Those are coming from these continuous time filters, and then MATLAB applies the bilinear transform for you and gives you the design of those. So if you've used those commands to make discrete time filters, the Butterworth command or the Chebyshev command or whatever, you're effectively doing what we're going to learn the inside operation of in the next note set. Okay, just a few things to tidy up before we go on into the more meat of this lecture, and that's this trick. It's common to study things that have been so-called frequency normalized, and I'll tell you what I mean by that in just a second. It just allows us to not worry about a lot of the numerical details of a filter and just focus on one particular type of filter or one particular setting, and then we can unnormalize it back to whatever we want. So here's the idea. So suppose you have some H of S analog filter, that's its transfer function, and maybe there's some characteristic frequency, usually a cutoff frequency or a center frequency or something like that. If we take this H of S, and everywhere there's an S, we replace it by S times Wn. So that's what I'm showing here. And we rename that with a subscript, capital N, to stand for normalized. Here's what ends up happening. We get this new thing. We look at its frequency response. I've just replaced S by J omega. So now I have omega times omega N inside my regular H. And all this does is it moves the characteristic frequency to be 1. So this picture looks a little weird just because I drew it freehand with PowerPoint, but here's the idea. If I plug 1 into here, right? So I'm looking at this thing at 1. What ends up happening? So there's a 1 there, there's a 1 there. It's this thing. Whoops, not that. Yeah, it's the H at omega sub n, right? Because if I put a 1 in here, I have H of omega sub n. So that's right here. So that just says that this operation maps this point to this point, and it'll map 2 omega n to this. So basically, in this case where omega sub n is bigger than 1, which is usually the case, it just squishes this thing in with a linear scaling. Okay, so that's all it does. Now you might say, why do we do that? It's just so that we can talk about these normalized filters. We can do all of our work in terms of the normalized filter, get a nice form for the normalized filter, and then you want a certain omega sub n, a certain cutoff frequency, a certain center frequency. You just can unnormalize it, so then you map it back to here. So in books that talk about the design of analog filters, they often just do all the development in terms of these normalized filters. And then say, aha, voila, we can map this back to, or not back to, but we can map this to whatever desirable cutoff frequency or center frequency that we want. So there's the normalization, and then here's the denormalization or unnormalization. So if this substitution normalized it, it's pretty obvious that this substitution put into a normalized filter will denormalize it, because now we've got the omega sub n being canceled by the dividing by omega sub n. So you take the normalized filter, make that substitution, and you're right back to where you would have started. Or, as I said, we often start with the normalized filter as taken out of a table in a book, perhaps, and then we can denormalize it to whatever we want. So it's just a convenient little trick, and it shows up from time to time, so I wanted to touch on that here. And some of the results that I show in this note set will be for normalized filters. Another common trick that helps is we work everything out for low-pass filters. Not we, but a book on analog filter theory. It would work all the transfer functions out for the low pass, and then say, hey, do I have to, maybe that they spent 3 or 4 chapters doing that. Do we need 3 or 4 chapters now to do high pass, and then another 3 or 4 chapters to do band pass? Nope. There are ways to, once you have the low pass, to just convert it into the other types of filters that we want. And so we do this on normalized filters. So there's another motivation for working with normalized filters. If we think about reciprocating omega, let's look at the picture here. So here's a normalized filter. There's our cutoff frequency for this one. Again, kind of a weird drawing. Remember, I just drew this arbitrarily for the unnormalized version, and then when I squished it to get the normalized version, it looked really weird. But anyway, there it is. For whatever reason, it looks like that. If we now reciprocate and look at the numbers between 0 and 1, if we look at 1 over omega for those are now going to go from 1 out to infinity. And if we look at the numbers from 1 out to infinity, those are going to go between 1 and 0. And so that's how we can take a filter and convert it from a low pass into a high pass. It's just reciprocating omega. And so that motivates what we need to do with our S. So we've got a normalized transfer function. If we take the S that's in there and replace it by 1 over S, we'll have a normalized high pass filter. So we start with a normalized low pass filter. Everywhere there's an S, replace it by 1 over S, and you get a normalized high pass filter, and now you can unnormalize that back to wherever you want. And there are versions for low pass to band pass, and I don't really cover that here. You can look it up. It's easy to find, but we won't really need it here, so I didn't cover it. And also, this is for continuous time. There are similar transformations for discrete time. So, in fact, if you try to Google this, most of what you'll find are the transformations for the discrete time version. So you might have to dig a little bit to find this continuous time low pass to band pass. But look in a book on analog filter design. I allude to one coming up. Okay. Now I want to take you through a few classic filter structures, and by structures I mean the transfer functions. So I should comment that there are 2 different structures of filters that we could talk about. One is just the mathematical structure. What does its transfer function look like? And then the other is kind of what filter designers call the topology. That's the circuit that's being used to do that. So we've got the transfer functions, and those are characterized with names like Butterworth and Chebyshev and elliptical and so forth. And then we have Topologies, those are characterized by terms such as like quadratic or biquad or salient key and things like that. So don't get those mixed up. We're not really going to talk about those topologies here because those are for building with analog circuits, and that's not what this course is about. So anyway, here is the simplest first order low pass filter. This comes from a circuit that looks like this. I just said I'm not going to talk about the circuits, and here I am talking about the circuits. And this omega sub c is equal to 1 over RC, and that's in radians per second. So you've probably seen this filter in your signals and systems class, I would hope. So I just wanted to link this math to this circuit. But there it is. We've got a cutoff frequency omega sub c. I'm not showing it as the normalized one here. So let's look at poles and zeros. The numerator is just a constant, so there are no zeros, or explicit zeros anyway. And then the poles, there's just one, and omega sub c has to be a real number, and should be positive to put the pole over here at negative omega c. So just one pole, and you may have done some Bode plots and know what this thing looks like from that, and know that we get this minus 20 dB per decade. And I'm showing two different examples here with omega c equal to 100 and omega c equal to 1,000 radians per second. And you can see that at omega sub c, this drops down to minus 3 dB below what is happening in the passband. So there's our favorite little low pass filter. And then we have a high pass filter. Denominator is the same, and we'll see that characteristic over all of these filters, that the denominator doesn't change to change the type of filter. It's just what's going on in the numerator, and that's kind of interesting. So poles still in the same place. This is our S-plane, by the way, J omega axis and the real sigma axis. The only difference is we now have a 0 at the origin. That comes from this numerator that's just an S. So set S equal to 0, and it has a 0 at 0. No kidding. And so what this does is it ties the frequency response down to 0 at omega equal to 0. Now we're on a log frequency axis here, so we can't show 0. But this thing just keeps going down and down and down. It will eventually get down to 0 non-dB, which is minus infinity on the dB scale. So that kind of makes sense. It'll take infinitely many decades to get down to 0, and we have to get down to minus infinity, and we're going down at, well, backwards here. We're going down, going backwards at 20 dB per decade. So high pass filter, low pass filter, and yeah, so this one, I'll draw the circuit for this, and I think this will be the last circuit that I draw here. This is the R and the C, and here's the input voltage and the output voltage. So that's what we have for that. And you can make these out of inductors and so forth as well. But these days, capacitors are much more common than inductors. Okay, second order low pass filters. Now this is not the only structure for a second order, but these are the most common structure. So if you start looking at Chebyshev type 2, you'll have a different structure in the numerator. In fact, you do have some zeros there, I believe. It's been a while since I've looked at that, but I think that is true. But this is a simple characterization. And look at that denominator. It's second order, and instead of putting this as A1 and putting this as A2 like we did in general, I've attached some specific notation here. We call omega sub n the natural frequency, and it shows up here and here. And we call zeta the damping ratio. And if you've studied control systems, you probably spend a fair amount of time fussing about damping ratios. And they show up here in this. But we'll quickly reformulate this into some other parameter, a related parameter other than zeta, that's better suited to audio filters and filters in general, whereas zeta comes in play better in control systems. But nonetheless, I'm going to start there. So we've got no zeros, right? No explicit zeros. I keep saying no explicit zeros. That just means, hey, as s goes to infinity, this denominator goes to infinity and the whole thing goes to 0. So it's not going to 0 because of an explicit root of the numerator. So that's what I mean by no explicit zeros. Let's look at that denominator, second order, so it has 2 roots, so 2 poles. And when we can show that when zeta is between 0 and 1, this polynomial will have complex conjugate poles. So you can do that just by applying the quadratic formula to this and then seeing the role that zeta plays. I do that in some of my notes in signals and systems. So if you want to see that, you can go back and find that in my signals and systems videos. But if zeta is between 0 and 1, we get complex conjugate poles. If zeta is equal to 1, then it will turn out that we have 2 real poles that are exactly the same number, right? So yes, a polynomial has to have 2 roots. And so if it's like, s plus 1,000 squared, then that has 2 roots at negative 1,000. So that's the distinction. So we call those repeated real poles. And then if zeta is greater than 1, we get 2 distinct real poles. So again, this can be puzzled out by looking at the role that zeta plays after applying the quadratic formula to the denominator. And here's a nice little plot showing those 3 scenarios. And obviously this is a range and this is a range, and I'm only showing one value in that range, and I don't remember the exact value that I used. But this shows the nature of it. Let's look at this complex conjugate pole case. In that case, we get a fairly pronounced resonant peak, and it gets more pronounced as zeta goes to 0. We'll see another picture coming up. And since it's second order, we get a 40 dB slope. In this case, it's minus 40 dB per decade because it's going down. Then when we have repeated roots, we don't get a peak, and things kind of just drop off, and we still hit this minus 40 dB per decade eventually. And then when we have the 2 distinct real poles, there's a break here, so that would be the case for the position of one of these poles, the lower one, and then there's a break here, that would be the other pole. So in that plot, we don't see the role of omega sub n explicitly, but it is really there. Those poles one's going to be on each side of the omega sub n, as we'll see on a subsequent slide. But for that case, look, it comes along, it hits that first pole and goes minus 20 dB per decade for a while till it hits the second pole, and then it picks up another minus 20 dB per decade to become minus 40 dB per decade. So just a good characterization to keep in your mind. Which should we use? Depends on what it is that you're trying to do. Although I will say in most audio applications, we're probably somewhere more around that range. Sometimes we want a little peaky thing, and we'll see that we can use that for like a wah-wah pedal or something like that. And sometimes we just want it to come out and roll off nice and smooth, and we don't want this intermediate. But could be whatever you want. The more you understand about this, the better you can design things to do what you want. Okay, Let's take a look at these pole positions. So here I was just showing, 3 different cases. I said this is a range and I'm only showing one actual position. What happens as it goes from near 0 to near 1? And what happens over here as zeta gets larger beyond 1? Well, that's what I'm showing here. This is what's known as a root locus plot, and if you've studied control systems, you probably have seen these things. But let's start over here with zeta equal to 0. Zeta equal to 0 puts the poles right on the j omega axis. So notice here I'm disallowing that case because that would give me a filter A that is marginally stable, and we generally don't like those, but also is impossible to actually build because you would need 0 resistance in all of your components to make that happen, including the wire, and that can't happen unless you're going to run your circuit at absolute 0. But we show it on the plot here just to show kind of where we start. And then as zeta increases, this thing moves in this direction. And we start over here with that one, and that one moves in this direction. And so we're, kind of following the path of the poles as zeta moves from 0 to 1. And then when zeta equals to 1, guess what? They hit right there. And now we have the two that are right on top of each other. That's the repeated poles. And that's path, I didn't quite make the plot here correct. Maybe, well, it's hard to tell. Is this distance here really the same as this distance? It should be if I made the scale of these axes the same. So this is half of a circle, and it has a radius of omega sub n. So this starts off at on the j omega axis at j omega n, and it ends up over here at minus omega sub n. Then they hit, and then they start to separate. One goes this way, and one goes this way. And there is a point beyond which that won't go, and that would depend upon the omega sub n value and so forth. But this one also, I'm not sure if that goes out to infinity or not. I'd have to look more carefully. But that's the basic idea. So this is looking at the pole positions as zeta is varied, but omega sub n is held fixed. And then here's another plot showing, what do I got here? 1, 2, 3, 4, 5, 6. 6 different values of zeta. So this is done for a particular value of omega sub n, which I guess was 1,000, 2,000, 3,000, 4,000, 5,000. So that was equal to 5,000 radians per second. And so let's start here with a very small zeta. We have a very sharp resonant peak. And it looks like it's at omega sub n. And it almost is exactly. So there is a formula that will tell you where the peak frequency is relative to the natural frequency. So don't think that the natural frequency is the location of the peak, but it's pretty damn close. And it's closer for zeta that are really small. As zeta gets a little bit larger, then we see that the peak is a little bit less than omega sub n. And we can see that right here for the zeta equal to 0.3 case. And even for the zeta equal to 0.5 case, you see the peak happening quite a bit away from the omega sub n. But really the peak is not very pronounced for that case. Okay, but for the most part, for small zeta, we can say the resonant peak is essentially at omega sub n. And then I showed 2 other cases here, 0.707 and zeta equal to 1. So remember, zeta equal to 1 was the repeated roots case. So we're only looking at one case for the repeated roots. And over here, I'm calling out special attention for the zeta equal to 1 over square root of 2, which is 0.707. So that's this red dashed curve here. That is the so-called Butterworth response, and we'll see that in subsequent slides. It's so-called maximally flat. That's why I put that in quotes. There's Butterworth used a particular definition for what he meant by that, and you can look it up. It involves looking at the derivative of the frequency response at omega equals 0. It's also monotonic, so it just goes down. Now the zeta equal to 1 also is monotonic, but it starts to drop off well before the cutoff frequency at omega sub n. That's the other nice thing. When zeta is equal to 0.707, it crosses minus 3 dB at omega sub n. So omega sub n is the cutoff frequency as defined as the passband edge, where it drops to minus 3 dB. So that's a common definition of that. So just keep that in mind, nice things to keep in your head as you're thinking about this. Here's that same root locus plot, at least up to the case of zeta equal to 1. But for the normalized. So if you go to our transfer function here, and we normalize that relative to omega sub n, then what we would get is something that looks like this. And you can see there now the omega sub n for this normalized filter is 1. So that means this has a radius of 1. So it's 1 out to there and 1 out to there. And in fact, 1 anywhere along that circle, which unfortunately I drew with different scales on these two axes, so it doesn't quite look like a circle, squished, I guess, a little bit. So I just threw that in there to show how we normalize one of these things and then look at it. So you'll often see in filter design books focusing on things that look like that, and then when it's all done, they say, oh, let's denormalize this. And in fact, they often will figure out how to implement that using some sort of circuit topology, and it will end up with so-called normalized components. So in some cases, that might be like an R of 1 ohm and a C of 1 farad. And then you get the denormalized filter, and you can see how those components map. And then so it's easy once you see the topology for the normalized filter, and then there's just a little formula that tells you how to adjust the normalized R and C to get any cutoff frequency or zeta or whatever you want. And we're soon going to replace this zeta by Q. We introduced Q in an earlier note set, and that is a nicer way to think about this for audio. And here it is. What a nice lead into this slide. Quality factor, or Q, and the damping ratio. So we just saw that zeta, the damping ratio, is what controls the amount of resonance that occurs. And we saw that as zeta gets smaller, that resonance gets higher, and we get a sharper peak here. Now we're looking at a low pass filter, but imagine a band pass filter. So we could characterize the sharpness of that peak by the bandwidth of that. And that's a place where Q really makes a lot more sense. But I am going to introduce it here for the low pass filter because sometimes we care about that as well. So we are now seeing two definitions of the quality factor. We saw it back a few videos, a few note sets ago, where we introduced it just as the idea for a bandpass filter, and now we're generalizing it and linking it to the damping ratio, and it can be used for high pass, low pass, band pass, etc. So this is the quality factor, or Q factor, it's just 1 over 2 zeta. Now, some authors, Zolzer in particular, at least in one of his 2 books, uses Q sub infinity. I don't really know why, but I'm just alluding to that there. So if we make this substitution, there's 2 zeta, so we replace 2 zeta by 1 over Q, so there's the 1 over Q. So now we get something that looks like that. Notice that zeta and Q are inversely related to each other. So remember, we got the spiky resonance when zeta was small. That means when zeta is small, Q is going to be large. So we'll see the spiky nature and the resonant nature when Q is large. And that makes sense from the way we defined Q before, where it was the center frequency divided by the bandwidth for a bandpass filter. And if we do this in normalized form, that will get rid of all these omega sub n's, and we end up getting something that looks like that. And again, this 2 zeta then becomes the 1 over Q. So that's a nice formulation. So, I say in some sense, zeta is more natural for the low pass than the high pass. But audio engineers still generally think about Qs for low pass and high pass. But here's our definition that we saw from before. And this comes from really where it first originated. People were looking at building bandpass filters to tune radios. And so FC was pretty high, and you wanted a very narrow bandwidth relative to that high cutoff frequency. So if you could get a high, or not cutoff frequency, center frequency, if you could get a high center frequency and a small bandwidth, this ratio was large, and that was viewed as a high quality bandpass filter for radio applications. And so that's where the name quality factor came from. And then people saw, oh, this is just linked to zeta, and it can be applied to low pass and high pass as well. So that's all kind of nice. So if you remember, we talked about constant relative bandwidth filters. Those were also called constant Q filters. And I'd like to point out that this definition of Q carries over to discrete time filters for bandpass filters, but we'll see that it's a little more cloudy as far as showing up in the transfer function for a general second order transfer function. So that part's a little funky. So let's just look at some other second order filters. So I should point out that for first order, all you can get is low pass and high pass, essentially. But once we go to second order, we can get a lot of different things, including these 4 classic forms: low pass, high pass, band pass, and band stop. So we've already looked at the low pass, and so here I'm showing the normalized version and the non-normalized version. You can see I don't really make a distinction in the notation, and in fact I think these were just copied out of one of Zolzer's books. I think I credit that somewhere along the line here. And this Q, yeah, you can see Zolzer using Q sub infinity, so clearly I just copied and pasted this from the book. To avoid having to write this out in equation editor. But as Q, or Q infinity, goes up, the poles move this way. We saw that, right? We saw that as zeta gets smaller, we moved in this direction, or as zeta gets larger, we moved in this direction. So that is consistent. Then we had the high pass. We haven't seen the high pass for the second order filter. We get an S squared, which puts 2 zeros at the origin. And so that's the characteristic for that. But the important thing to note is it's the same denominator. So the poles do the same thing. So the difference between low pass and high pass is just driven by the behavior of the poles, or I'm sorry, the zeros. And then we get bandpass. Now, this is an interesting one. It's not terribly obvious from this viewpoint why this would go up, go flat, and then come back down. Or it might not really go flat for any period of time, but go up, have a pass band that could be very narrow, and then go back down. If you analyze this from a Bode plot point of view, maybe you've seen that. If not, you might want to review that. We've got what I call a starting slope term. So that will start going up. And then we have two poles down here. And so we would hit, let's first just think about those poles being real valued. So then, they've kind of come out and moved like this. Then we would hit one and then hit the other. And that's kind of how we think about it. Or we could think about those being complex poles, whoops, as we're showing there, in which case we would hit here and then we would get the full change of minus 40 dB per decade. So we're going up at 20 dB, then it changes by minus 40, so we immediately start going back down by minus 20, but then there's a resonant peak, and that would make a very sharp, peaky bandpass filter. So that's how we would see that this structure actually gives us a bandpass filter. It's that S in the numerator that gives it to us. And then we've got bandstop, and that one's really easy to see. So we've got a 0 at omega sub c. So right there is a 0. And if we evaluate this on the j omega axis to get the frequency response, we see that, we get a 0 right at omega sub c. So it's going to pull the response down. But also moving this pole back and forth will make that notch either broader or sharper. So let's get into Butterworth filters. As I said, those things are maximally flat. I put it in quotes because there's a precise definition of what that means, and I'm not going to go into that here. But for our purposes, the big thing is that it has no passband ripple, which is often good in an audio setting. And so, again, without going into the details, this is what Butterworth proved long ago, back before transistors. So this was all ultimately implemented for the first time using vacuum tubes way back. I think maybe it was in the 1920s or something like that. But Butterworth worked out the math and showed that to meet his requirements that he defined as maximally flat, the normalized version of the filter should have that form. So this was for the nth order filter because that forms an nth order polynomial. And so that leads to, for n equal to 2, we would have a polynomial, a second order polynomial in S here, which would have two poles. And if you work that out, you'll find out that you get two poles right in these positions. So I think this angle psi, I think it'll be clear as I show the rest of the things here. That's the 45. So yeah, plus and minus 45 degrees from this sigma axis. So that would be the Butterworth filter, second order. That would give you that zeta equal to 1 over square root of 2. And then you can figure out what the Q is, right? Zeta is equal to 1 over square root of 2, and Q is equal to 1 over 2 zeta. So 2 zeta would be equal to square root of 2. All right, yeah, so Q then is also equal to 1 over square root of 2. So interesting for the Butterworth case. Zeta and Q are both equal to 1 over square root of 2. So that's the n equal to 2 case, and the denominator of that would look like this. Remember, this is for the magnitude squared, so we have to do a little bit of work to go from that to the denominator of the S. But I think you can probably figure that out, but it's not terribly important if you go through those steps or not. Just recognize that that's coming from our form before. And so this is normalized. And yeah, remember this was 1 over Q. So Q is 1 over square root of 2, just as I scratched out there. So zeta is equal to 1 over square root of 2. And then here's some other orders. I didn't show the third order, but I showed fourth, fifth, sixth, and seventh orders, and I showed what the angles are here. So plus and minus 22.5 to those, and plus and minus 67.5 out to those, and then so on and so on. These plots come from a book called Design of Analog Filters by two authors, Schaumann and Van Valkenburg. If you find an older version of this, it'll be just by Van Valkenburg. But then he passed away, and Schaumann, I think, was one of his students, maybe, took over making revised editions. So if you're going to get a book on analog filters, this is probably the one to get. It's been around for decades and decades and decades. It is the classic book. But anyway, you can see that for Butterworth filters, these poles lie on a circle. A circle of radius, in this case, equal to 1 for the normalized one. So this is not the root locus that we were looking at. This is not movement of poles. This is, in this case, 7 different poles circled around those. Because remember, zeta is not changing here. Zeta is set to give us the Butterworth maximally flat structure. Okay, so that's that. And then this is from Zolzer's book, just showing second order and fourth order for low pass and for high pass. So we've seen this structure just now, and no surprise, we just put an S squared up there to get the high pass version. Now, what might seem odd is for the fourth order, Zolzer is showing this factored into a product of 2 second order stages, and that's because that's how these things are normally implemented. So fourth order filters in analog are generally implemented using a cascade of 2 second order stages, and we use electronics to buffer between those stages, because if you take one circuit with a transfer function and another circuit with a transfer function, even though in theory we say the cascade of systems is the product of those 2 transfer functions, that doesn't quite work when we do it practically with circuits, because there is the input impedance of the second stage is affecting the transfer function of the first stage and vice versa. So we often use op amps or transistors or JFETs and things like that to separate these 2. Now, you might think that to get a fourth order, you would just take 2 second orders and cascade them, but that's not true, right? If you did that, go back here, you'd really just get a double pole there and a double pole there, but that's not what we need. So you need to tweak those. And so this one will give 2 of those poles, and this one will give the other 2 of those poles. So that's how it works. And then, you can look in, you can look in this book to see how one might actually implement this kind of stage. So that's that. But this is digital audio signal processing. So we want to do this digitally. And it turns out that we often do digital implementations with a cascade of second order stages, but not because of this buffering needed. It has to do with sensitivity to the coefficient quantization. And that's something that's important in implementation of audio filters. I'm not going to go into it in this course, but find a good DSP book, and there's always a chapter in there about the effect of coefficient quantization. Read that chapter and you'll have it. Here's some examples of low pass and high pass Butterworth. Might be a little confusing. This tail over here is the low frequency part for these two low passes. And then this part over here is the high frequency part for the two high passes. So just orient your mind to that. I just borrowed this from Zolzer's DASP book. Probably would have been convenient to make them kind of color coded or something like that, but I didn't take the time to do that. Here both high passes have a cutoff frequency of 50 hertz, and the low passes have cutoff frequencies of 5 kilohertz, just for convenience to show. And we're plotting it on a log frequency axis with the marked frequencies being 20 out to 20,000. That's a common thing for audio, even though generally we mark the start of the decade. So that would be 100 and that would be 1,000. For audio, we often don't do that. So you can see that the roll-off for the second order is less steep than the roll-off for the fourth order. So if you really want a filter that really gets aggressive, you need to go to higher order filters. That's the same, continuous time or discrete time. Okay, shelving filters, we talked about those before. They're used in audio equalizers, and in particular parametric audio equalizers. And remember, they boost or cut some band, and they leave the rest of the band untouched. So I'm just showing those here. That would be this response, which would stay like this, or this one would be this response, which would stay flat like this over all the other frequencies. So how do we characterize those? Well, let's start with a first order one, and we'll start with a normalized cutoff because it's nice to work that way. So here is a low pass filter with a gain attached to it, G0. And let's not worry too much about the values that gain can take, but it can take on positive and negative values. So what we're doing is we're sending the signal straight through. So there's no filter at all. And we're sending the signal through a low pass filter. And then the part that comes through the low pass filter is added back into the original signal. So that's this part. So you can kind of think we've got the full original signal, and then if G0 is positive, we're adding in the low frequency content of the signal. And if G0 is negative, we're kind of subtracting that out to get some sort of destructive interference at those low frequencies. So that's kind of how that makes sense. But this isn't how we really want to implement it. So let's manipulate that. With just a little bit of algebra, we can get this into this form, and V0 is now 1 plus G0. Now, once we have it in this form, we no longer care about this G0. We'll just focus directly on V0 and think about it that way. So the G0, it might pop up occasionally in subsequent notes, but it's V0 that we care about once we get it in this form. So let's take a look and just verify that this is doing what we want it to do. If we look at the gain at omega equal to 0, well, that would be S equal to 0, so that's gone. We get V0 over 1. So the frequency response at low frequencies is going to be equal to V0. That's why this V0 is kind of the important physical parameter that we're interested in, and we don't care about G0. Well, it turns out that if we analyze this further, and I'll show you an example, I think, on the next slide. This works really well when V0 is greater than 0 dB. Now, warning, V0, the number that we put in there, is not in dB. So I really mean when V0 is greater than 1 non-dB. But we like to talk about these parameters in dB. That's what audio engineers do. So that would give us a boost at low frequencies. So greater than 1, that means G0 is a positive number. So we're adding in some additional signal components at the low frequencies to what was already there. But it turns out it doesn't really work well for the cut form, where V0 is less than 0 dB or less than 1 in non-dB form. And so we'll use this form, as we show here, just for the boost, and then we'll fix it so that it will work for the cut. So here's a response plot. This is the frequency response, and I'm showing it for V0 greater than 1 and V0 less than 1. That would be these those 4 plots. You can see that doesn't quite work. But look at the ones up here. Those work nicely. I should have showed this. This plot is coming from Zolzer, but these values here, as we just proved on the previous slide, will take on, since this is in dB, will take up on the value of V0 in dB. And by the way, I don't know what these little circles are there. It's not saying degrees. It just came over when I took a screenshot from the Zolzer book. It's not in the actual book, but when I brought it over, it was there. I could have tidied it up, but I didn't. So here's how we're going to fix this issue, the fact that we don't really get a cut as we would want it to be. We're going to flip this transfer function. If we flip this around, let's take a look at what we get. Now we have this transfer function, and notice that I'm labeling this B and this C. So this is the boost version of the low shelf and the cut version of the low shelf. Now when we let V0 be greater than 1, we get all this stuff going down. And that makes sense, right? When you reciprocate something and then write it in dB, it's really the negative of the dB. So reciprocating non-dB corresponds to negating in dB. And so that's why these things come down here to their negative values. So now we have 2 different forms, and if we want, say, a -10 here, we would not put in V0 that corresponds to -10 dB. We would put in a V0 corresponding to +10 dB and use the cut form, and we'd get a -10 dB V0 value or gain value at the low frequencies. So that's kind of annoying. And in the analog world, I guess you have to have 2 different circuits and switch between them. To be honest, I've not worked in the analog audio world. To be even further honest, I've not worked professionally in the audio world at all. I've only delved into this stuff because I play music and I like audio, and I'm a digital signal processing guy who does other things professionally, but wanted to learn about this. So I learned about it, and now I'm sharing what I learned with you. So I don't really know how they do this in the analog world, but my guess is they have 2 different circuits to do that. I know how it's done in the digital world. We'll see that. So how do we implement this? In discrete time world, there are some clever ways that we can do this, and it's all programming, so it's much, much easier to handle these kind of what I call exception processing kinds of things. So both of these, we've got the boost version and the cut version. Both are specified for V0 greater than 1. They both have a single pole and a single 0, right? Because we've got a polynomial, first order polynomial in both numerator and denominator. So for the boost version, we've got a pole that's fixed here, and we've got a 0 that's going to be moving. So as I increase V0 above 1, it starts down here and moves out that way. And so that's how that would work. And then it's pretty clear over here. Now I've got a 0 fixed here. So instead of a pole, I've got a 0, and it's the pole that moves as V0 goes. So that makes complete sense. So, so those were first order low pass or low shelf, and we did it all with normalized cutoff. So now we can just use the same idea as we did for the low shelf. We can do the high shelf. I suppose we could do the frequency or the low pass to high pass flip here. We could do that as well. But we're just going to start with, to see it more generically, we're going to start with a high pass filter there. And after a little bit of algebra, we end up with something that looks like that. Let's just check. As omega goes to infinity, we see that this term will dominate that, and this term will dominate that, and then we get an S that canceled, and we're left with V0. So at high frequencies, and again, this is the boost form, at high frequencies, it will shelf off at a value of V0, and we would normally show that in dB. And we have the same exact asymmetry issue again. So it doesn't work for V0 less than 1 as we might expect it to, but it doesn't. So we flip the transfer function and we get the cut version, and then we can look at poles and zeros, and we see something like this. And now we see that for the boost, we have a fixed pole there, and the 0 moves back and forth in that region between where the pole is and here. And then for the cut version, the roles of the pole and 0 are interchanged. So those are first order, and for second order shelving filters, we could go through all the same development and end up in the right place. But what we're going to do is just take insight from our pole 0 plots for the first order shelves. So if we go back here, let's just go back to the first order low pass or low shelf. So we had, think about the pole and 0 are on the same line. So it kind of makes sense. And like I said, you can derive this if you want, if you don't believe it. But we are saying, well, we're going to have a pole. We have to have 2 poles, so they could be complex like that. And then the 0 would lie on a line, and the 0 would lie on a line. And then it's pretty obvious to deduce the roles get interchanged for the cut. And so we end up with this. So that is our form for the normalized boost and cut versions of the low shelf. And then similar kind of thing, we can deduce the form for the second order high shelf. Same kinds of arguments. The things that move are inside here. And just like we saw for the first order high shelf, except only 1 pole and 1 0. So we almost automatically get the right structures. Again, you can derive these if you want. But let's just think about these transfer functions. How did I deduce what these things should be? Well, again, we could go through all the math, but we can also just kind of deduce this by starting with the Butterworth denominator and figuring out what I need in the numerator, right? Because all these are based upon Butterworth filters that we're assuming make up the role of that low pass filter. And so this, using Butterworth here, is kind of the classic for the shelf filters. Now, I do point out that in Zulzer's DASP book, he puts this as B0 and this is B2, which is kind of backwards from the standard. So I'm following the standard here. So if you look in the DASP book, you'll see that my B2 is his B0 and so on. So we do know that we need poles here that look like that. We can just factor that and find where those poles are. But we also know that from our study of pole locations for Butterworth, Now we can also see that in order to make the filter gain, remember this is a low shelf, so the filter gain should go to 1 as frequency gets high. So let's look at that. As frequency gets high, these are going to dominate their respective terms, and then the s squareds cancel, and so that has to be equal to 1, so B2 has to be equal to 1. These are nice little analysis tricks that you can use to figure things out and or to just check the sanity of your solutions. We also need B0 to be equal to V0, and we can see that because as we go to omega equal to 0, that means all the S terms go away. We end up with being B0 over 1, and so if we want that to go to V0, we need B0 to be equal to V0. So we've nailed down B2 and B0, and now we know that the zeros have to lie on the same radial line, and they have to lie on a radius, a circle of radius square root of V0. We know that, and from that we can deduce that the zeros have to be at the same angle as the poles with that radius, and therefore those are the locations of the zeros. And putting all that together, we can deduce that the structure looks like that. So again, we could have gotten there by just starting at the beginning and working through all the math, but this is nice. It's nice to be able to kind of figure these things out in a little more intuitive way. And now here I'm going to just simply apply the low pass to high pass form. The low shelf is built from a low pass filter, and so when I apply this transformation, I'll get that'll convert into a high pass filter, which will give me the high shelf form. So just doing this change on this and then doing some algebra to get polynomials in S, I end up getting this form. And so those give us the boost forms, and then same trick is needed. Flip them to get the cut versions. And so here are some plots showing that, and I guess I should have said, as should have Zulzer, and maybe he says it in the book, I should have said what the V0 values are to achieve these levels, but they're correct. Okay, so there we go. Peak filters, so moving into the inside of our parametric equalizer. We've seen those already. So let's start with the boost form and the normalized cutoff. We've been down this road, so we kind of know the tricks already. And so we're going to find the boost form and just flip it to get the cut form. So we're going to start with the same idea. Let the whole signal go through one path and then put it through a band pass to isolate out the things that we either want boosted or cut. And, at least initially, we're thinking that we do the boosting or cutting with that G0, but it turns out that we just do the boosting with that. And if we start with our bandpass form, using Q rather than zeta, nice convenient way, again, this is all normalized, we end up with a transfer function that looks like that for the boost form of the peak filter. And so now notice that there's two parameters involved here, the gain level and the Q. That will set how sharp the peak is, as we'll see some plots. And this would work for V0 in non-dB greater than 1, and that's going to set the peak value. And Q is going to set the relative bandwidth of this. And again, I'm just pointing out that if you know that you want a peak of PdB, so you want a peak of 20 dB, you'd put in 20 there, divide by 20. So 20 over 20 is 1, 10 to the 1 is 10. So you'd set V0 equal to 10 to get 10 non-dB to get a peak level of 20 dB. So that's how that works. So there's what we just developed. That's for the boost. And now we can look at the role of the poles and zeros. Notice that the poles are fixed, right? We set Q, And then we're thinking about changing V0. So as V0 changes, the zeros move. So it's a little, looks like maybe that arrow might be associated with the pole, but it's not. It's associated with the location of the 0. And so in principle, those zeros can come in here and then go in each direction. So those complex poles move closer. The complex pair of the poles move closer to the j omega axis. So these poles would move as Q changes. So as Q gets larger, the poles move closer to the j omega axis. And then if we set V0 equal to 1, puts the zeros on top of the poles. And we wouldn't really want to try to do that in a real circuit. That's just going to have poles and zeros cancel, and it would be perfectly flat at 0 dB gain everywhere. If you were implementing this, you'd probably switch out the circuit, or at least switch some components out due to tolerances of the components. And we can also see what happens as V0 changes. We're indicating that happens over here. In the DASP book, Zolzer says that the zeros are complex, but I mean, in reality, they do start to go back out like this. You might not want to operate your circuit that way, but that does happen. Okay, now we just flip it to get the cut form. Everything else stays the same. V0 is still greater than 1, but it's going to give us a negative dB value for the peak. And the rules of the zeros and poles are interchanged now. And so I'm just going to go through this quickly. You can read all this, but it's same as before. Here are some pictures showing some scenarios. So remember, we have to use a different transfer function for the boost and the cut form. And so this is showing peaks at those values with FC and Q fixed at those values. So, you know, not a terribly large Q value. We'll see a larger Q value as we go on. Now we're fixing the boost and cut at 16 dB. The cutoff frequency is set at 500 hertz, and we're looking at a variety of Q values. So this would be the 0.707, and this would be the 3.5. So as Q gets larger, the peak gets narrower. And you can go to much higher values than that. You know, Qs of 10 or more might not be uncommon if you want a really narrow peak. So you could make plots to explore that. And then this is keeping Q and the boost and cut fixed and looking at different center frequencies, F sub C. So in application, you'd have the three knobs. You'd have FC, you'd have a boost cut, and you'd have a Q knob, and that would make a peak filter one peak filter in your parametric equalizer. All right, so hopefully this gave you some insight to analog continuous time filters. We'll build on this as we go on into discrete time. In the next set of notes, we'll look at how to, we'll look at this thing called the bilinear transform that will allow us to take any analog filter transfer function and convert it into a kind of equivalent, pretty much equivalent, discrete time transfer function. And that's what we're interested in this course. So hope to see you there.